If you have successfully identified some interesting executable binary in the firmware file of your device, and if you want to run it or reverse engineer it in a debugging-friendly, reverse engineering-friendly emulation environment, this is the video for you. We will talk about using QEMU as an emulation environment reasonably similar to our device, where to run, debug and reverse engineer interesting device executable binaries. QEMU can quick emulate hundreds of different CPU architecture, and it is the most important building block of our emulation environment. I am Valerio Di Giampietro. I am an electronic engineer with a background in digital electronics and information technology infrastructures. I would like to be your friendly Italian hacker neighbor willing to share with you tools and techniques for hardware hacking that I learned by myself hacking many devices. If you have not done yet, please subscribe and click the notification bell below to be notified when new episodes will be released. And now, let's start! This is the 7th episode of the series Hardware Hacking Tutorial. In this complete series, we will talk about the hacking process based on information gathering from our device, building an emulation environment where to run interesting binaries, discovering how the device works, and then hack the device and modify its firmware. This episode is about QEMU setup. This is the first step in building an emulation environment. We will talk about the requirements for the emulation environment, the different QEMU emulation modes, and how to emulate an entire board that is reasonably similar to our IoT device. We will also introduce a tool for building the kernel and root file system of our emulated board. In this episode, we will use as an example the same sample Gemtech router we used in the previous episodes. We want to have an emulation environment that can run the device executable binaries we are interested in. This means that our emulation environment must have at least the same CPU architecture and instruction set of our device. We will not be able to entirely emulate our device with all of its internal components and peripherals, like in our case the Ethernet switch included in our router, or the VoIP chip to drive a plain old telephone system set, or the specific Wi-Fi chip, but we will be able to emulate a reasonably similar board that can run the executable binaries we are interested in. There is a fantastic open source software that can emulate hundreds of different boards with hundreds of different CPU architecture, and it is also very efficient and quite fast in the emulation. It is QEMU, the quick emulator. There are many other emulators, but many of them are not free. Some of them are more specialized for a certain architecture, maybe more accurate for that architecture, being able to emulate each CPU cycle, but for our purpose, QEMU is by far the best emulation software. Installing QEMU on a Linux PC is easy. You will find some instructions in the description below. QEMU has 3 modes of operation. A system mode operation. In this mode it emulates an entire system, an entire board, with a certain type of CPU, a certain amount of RAM and disk, with some other chips like EEPROM and so on. You can only emulate boards already included in QEMU, unless you want to modify its source to add additional boards. This is not impossible, but it has a quite steep learning curve. QEMU has also a user mode operation. In this mode, it doesn't emulate a different board, but does some sort of machine code translation from the machine code of, for example, a MIPS or an ARM executable binary to the machine code of our x64 Linux PC. It does a good job at mapping original kernel system calls to system calls in our x64 Linux PC. It is a useful operation mode because it can be used immediately without building a full emulation environment, but sometimes it can run our device executable binaries, and some other times it can give weird results. We will see an example very soon. The last QEMU mode is the virtualization mode. We are not interested in this mode because it is used to run a virtual machine in our PC with the same x86 architecture. This is the mode used by the KVM and Xen virtualization environments. The QEMU user mode is the simplest mode to use, but we need to know the CPU architecture of our binary file. For example, in our sample Gemtech router, we have seen in the previous episode the assistant executable that is used to generate the Wi-Fi password. We have a copy of the SquashFS root file system of the device in our Linux PC. We can easily understand the binary file architecture with the file command. In this case, the file command on our executables tells us that we have a 32-bit MIPS architecture with an LSB, least significant byte first architecture, also known as Little Endian. The user mode QEMU emulation commands have the format QEMU processor architecture. So in this case of MIPS, we have available 6 commands shown on the screen. But which one is the right one in our case? We have a 32-bit architecture, so we can exclude the 64-bit commands. The N32 architecture is a specific MIPS architecture that has the most 64-bit capabilities, but use 32 bits data structures to save space and process time, and it's not our architecture. We have an LSB or Little Endian architecture, so we have to use QEMU MIPSL. Why the EL suffix means Little Endian? It seems that it is the initials of Little Endian written in Little Endian order, with the last significant char first, a joke that only nerds can like and understand. If we try to execute the assistant program with the QEMU MIPSL command, we receive an error about the muslibc file not found. We have to use the -L option pointing to our device root file system that we extracted in the previous episode. If we look at the QEMU MIPSL man page, we can see that the -L option specify the ELF interpreter prefix. What does mean interpreter prefix? It is clear what an interpreter means in the case of a script, like a shell script, where /bin/sh must be executed to run the shell script, or in the case of a Perl script, when user bin Perl must be executed to run the Perl script. In the case of an ELF binary file, it has a similar meaning. The binary file usually includes a call to shared library functions like open to open a file, printf to print a string, and so on. These shared library objects will be linked at runtime, replacing the references in the binary file with the actual memory address, after having mapped this shared code to the address space of the current process. The interpreter in the ELF file is the dynamic linker that has the responsibility to do these references to memory addresses mapping. Without it, it's impossible to execute the binary file. Only binary files that have been statically linked and that have no references to shared objects don't need an ELF interpreter. With the -L option, we tell QEMU MIPSL command the prefix to use every time in the ELF binary there is a reference to the interpreter or another library file. By the way, we can look at what is the interpreter of an ELF file using the readelf command with the options -L to list only the ELF header, and we can confirm that it is muslibc for the bin assistant executable and for other executables of the same device. If we do another unrelated example on our Intel Linux box, we can see that the interpreter for the ls command on our Ubuntu 18.04 is LD Linux. If we look at the man page of LD Linux, we can see that it is the dynamic linker. Now we can run again the QEMU mipsel command with the -L option pointing to the current root directory of the extracted root file system of our device. We execute the same command we executed on the real hardware in the last episode. We pass to it the same parameters and we can see that it runs correctly, generating our default router password. We have only to convert the password to lowercase as seen in the previous episode. QEMU mipsel has also the possibility to be remotely controlled by the GDB debugger, allowing to debug a program for an embedded processor in our standard Ubuntu PC. Anyway, as I told before, this QEMU user mode emulation can be useful to quickly look at what some simple command does in our device, but can also have weird behavior. For example, if we use the command uname -a, we get a weird result. The information is exactly that of our Intel Linux Ubuntu machine, but it seems that it is a MIPS processor. Other commands can give quite confusing results or no output at all. For example, if we execute shellout, the other binary executable we are interested in, the one that has replaced the Linux standard blogin with the program giving a challenge code, in this case we don't receive any output. Overall, we can say that the QEMU user mode can be sometimes useful for a fast hardware, but it is very far from being a useful emulation environment. For this reason, we have to use the QEMU system mode to emulate a complete system. To emulate an entire system in QEMU, first of all, we have to choose one of the boards available that has the same processor architecture as our IoT device. In our case, we need a 32-bit MIPS processor with a Little Indian architecture. The QEMU command to emulate an entire system have the format QEMU-system-processor architecture. In our case, the command is QEMU system mipsel. To have a list of available boards with this architecture, we can execute this command with the option -M help. Unfortunately, not every machine listed by this command is well documented. You can look at the QEMU user documentation, link in the description below. Anyway, a good starting point is to use the default machine. Sometimes the default machine will reproduce configuration and limitation of a real board. For example, you cannot assign more RAM than the amount of RAM available on the emulated board. If you need to overcome these limitations, you can choose a more generic machine that doesn't reproduce an actual board. But if you change the emulated board with the more generic one, often you have to change also other parameters, because some parameters and related values are supported by only some boards. We can have a list of available processors with the option -CPU help. Usually a good starting point is to not explicitly specify the CPU model. In this way, QEMU will use the default. We can have some information on the available CPU variants on the QEMU user documentation. To emulate an entire system, emulating the board with the right CPU is not enough. We also need a kernel and a root file system. We cannot use the same kernel as the one we have on our device for multiple reasons. The kernel includes device drivers for our IoT device hardware, but not for the emulated board. This means, for example, that the drivers for the UART interface will be different, because also in the rare case that both of them use the same UART hardware, the related registries to drive the UART interface will be different. The result is, also if the IoT Linux kernel works, we will not be able to see any output and to give any input in our emulated environment. Unfortunately, the embedded world is different from the Intel PC world. In the PC world there is a lot of standardization, and the Linux kernel running on a PC will run on almost any other PC manufactured by one of the thousands PC manufacturers. In the embedded world, each system on a chip part number is designed assembling a CPU processor and many peripherals without any standardization whatsoever. To mitigate this mess, in the recent years, Linux has introduced the kernel device tree, that is a text file describing the board hardware in a standardized format. The kernel, when booting, will load this text file and will adapt its generic drivers to the actual hardware available on the board, for example, understanding what kind of UART is available and the addresses of the related registries. Unfortunately, very few boards use this methodology, and also when used, it would be a very difficult task to rewrite the kernel device tree for a different board as the one emulated by QEMU, and some key drivers could be missing anyway. Another minor issue is that the kernel available on our IoT firmware is usually in a special format to simplify the job of the bootloader. In our QEMU environment, we don't have a bootloader. The job of the bootloader is done by QEMU itself. This means that we should convert the kernel file format in one of the standardized formats that QEMU wants. The conclusion is that we have to rebuild the kernel for our emulated board. In our sample Gemtech router, the kernel is a version 2.6.36 that was released in 2010. We want to keep the same kernel version as the one we have on our board, and we want to configure our kernel with the same known options that we have on our board. For example, it is better to have the same preemption model that we have on our device, if we know it, or to include the same NAND drivers and the same file system support. Sometimes we don't know exactly everything, so we build a kernel and later, if we find some issues during our analysis, we will change some configuration options and we will rebuild the kernel. We also need a root file system. Probably we could use the same root file system available on our device, but it will not be debugging friendly or reverse engineering friendly, because usually this file system will not have many commands that we need for debugging and reverse engineering, like GDB or GDB server or strace, etc. And all of the executable binaries and libraries have been stripped. That means that they don't have symbols to help in debugging and in reverse engineering. Our idea, instead, is to build a root file system with every executable binary and every library compiled with debugging information. In this way, when we want to reverse engineer an IoT binary we are interested in, we can execute it with GDB, the GNU debugger. We can put breakpoints on each shared library function entry, and we will be able to understand the parameters passed to each library function call and the value returned. This will be possible only with open source libraries like libc and many others, and not with proprietary libraries, but this will be anyway invaluable in helping the reverse engineering project, as we will see in future episodes. To be able to run our IT executable binaries, we have to build a root file system reasonably similar to the one available on our device. This means that we must have the same dynamic linker and libc version we have in our device. The version shown here is that of our sample Gemtech router. It is MusiLibc, that was very popular in embedded devices because it is a sort of stripped down libc library that implements almost everything that libc provides, but with a much smaller memory and disk footprint. This version was released in 2012. Other libraries with the same version or compatible versions as in our device, especially the libraries used by the executable we are interested in. We can get the list of library files used by the binaries we are interested in with the readelf-d command. It can be not immediately easy to find the name of the related package and its version from the output of the previous command, but with the help of the ls and strings command and some Google search, we can find the related package and its version. For example, in our case, libc.so.0 is part of the same musilibc package above. libcrypt and libssl are part of the same libssl package version 1.0.0 that was released in 2010. It is important to understand that library files have the format libfoo.x.y.z, where .x changes when the new version has an incompatible application binary interface with the previous version. .y changes when new features are added, keeping backward compatibility. .z changes mainly for bug fixes and code improvement, but don't change the application binary interface. In our case, we want to include in the root file system the same .x and .y releases of the open source library used in the executable binaries we are interested in. If this is not possible, we could try to keep the .x released and a higher .y release. A lower .y release could work only if the application we are interested in will not use the new features introduced by subsequent releases. We can see that in our sample router, the versions of the kernel and the libraries are very old. This Gemtech router was manufactured in 2017 and distributed for a couple of years, but it has a kernel that was 7 years old when the router was manufactured. The musilibc was 5 years old, the libssl was 7 years old, and most of the other software has more or less the same age. Unfortunately, this is quite a common situation in the embedded space. Probably the manufacturer that has a very strong pressure on costs try to save some money in the development phase, reusing what it already has from previous projects, recompiling everything for the new device, but without upgrading versions because it requires much more time and costs. Sometimes the manufacturer reuses the same software development kit provided by the system-on-a-chip supplier, which is usually very old. This is a very bad thing from a security point of view, because there is a high probability to have unfixed critical vulnerabilities in our IoT device. Often it is possible to hack a device analyzing the software version of what is running, checking on the internet if there are critical vulnerabilities, and exploiting these vulnerabilities. To build the kernel and the root file system, theoretically we could build everything by ourselves. Everything we need is open source. The cross-tool chain to compile everything for our target architecture in our Linux PC is freely available, but this approach has few problems. It's not easy to choose and include everything we need in the correct version in the file system. And keeping track of version interdependencies between packages, libraries and the kernel is a real nightmare because of the so-called dependency hell. For this reason, it is much better to choose a build system, a software that helps us to configure the kernel for the emulated board that allows us to choose libraries and packages and that automatically builds for us the kernel and the root file system, keeping automatically track of the interdependencies. There are three tools that are quite popular in the open source world to build the kernel and the root file system for an embedded device or for a QEMU emulated board, that from the tool perspective are the same thing. The Yocto project is probably the most used among the professional embedded developers. It is very powerful. Not only it creates a kernel and a root file system, but it can create a custom Linux distribution with the software repository and the package manager, but it has a steep learning curve. Another popular tool is Buildroot. It builds only the kernel and the root file system, but it is much simpler. It is fast and easy to learn and has a very good user manual. The last popular tool is OpenWRT build system. It is the build system of the open source router operating system project. It was forked from Buildroot more than 15 years ago, and since then have significantly diverged. It is tailored to build a replacement router firmware. It has a lot of documentation, but in some way this documentation is scattered in its website, and for this reason requires more time to learn compared to Buildroot. For this training tutorial I choose Buildroot. In the description below you will find the link to the kernel and root file system image that we will use now in QEMU and that I will build with Buildroot in the next episode. I will describe how to build these images in the next episode. So we have built VM-Linux, the kernel, same version as in our sample Gematec router, rootfs.x2, it is the root file system image using the popular and simple x2 file system. If we want to add some more files or modify something, we can mount this image on our Ubuntu PC, hopeful when it is not used by QEMU, makes modifications and then unmount it. To emulate our MIPS Malta board with QEMU, we will use the QEMU system mipsl command. It has a lot of possible parameters and can be quite difficult to understand how to use them. The related man page lists all the possible parameters, but it's not always easy to understand its explanation. We will emulate our MIPS Malta board in QEMU with the following command that, for simplicity, we put in a shell script called qr.sh. qr stands for QEMU run. The environment variable QEMU audio driver is set to none to remove QEMU's startup warnings related to the missing audio driver. The options -M set Malta as the emulated board. The backslash at the end of the line means that the command will continue on the next line. The option -m256 sets the memory size to 256 MB of RAM. This is the max amount of RAM supported by the Malta board. The option kernel VM-Linux sets the file name VM-Linux as the Linux kernel. The option menonographic tells QEMU to not start a graphical user interface but to emulate the board using the terminal for input and output. I prefer this configuration because sometimes I access my Linux PC through an SSH terminal session. The option -HDA rootfs.x2 tells QEMU to use the file harddisk0 image file. The -netnic option creates a new virtual interface card and specifies model. The related driver must be included in the kernel. The -net user option uses the user mode network stack that doesn't require root privileges to run. With this option, a normal user can emulate the board, and the board will have a virtual interface that can communicate with the QEMU application. The host forward option tells QEMU to accept a connection on port 2222 and forward it to the guest port 22. This will be used to log in via SSH. We have to assign a non-empty password to root to allow SSH connection. The other host forward option tells QEMU to accept a connection on port 9000 and to forward it to the same guest port. This will be used to allow a GDB connection to the GDB server running inside the guest. The -no reboot option tells QEMU to not reboot the machine when it is halted, but to terminate instead. The -append option is used to append a command line to the kernel in a similar way that the group bootloader does on our desktop Linux. In this case, this tells the kernel to use the emulated hard disk as the root file system and to use the emulated UART as the serial console. We can now execute this script and launch QEMU emulating our motherboard. We can see the Linux boot messages printed on the emulated serial console, and finally we receive the login prompt. We can use the username root without a password because the image has been built in this way. With ifconfig we can see that it has correctly emulated the Ethernet interface. We cannot ping a host and also on the internet because QEMU, that is forwarding packets from the guest, is running in user mode and doesn't have the privileges needed to send ICMP packets required by ping on behalf of the guest. Anyway, we can normally access the internet. For example, wget can successfully download the index.html Google page. uname-a gives the hostname and kernel version that is the same as in our sample Gemtek router. cat proc CPU info tells us that we have a MIPS single-core processor. In QEMU we can emulate processors with multiple cores, but this usually slows down the emulation. cat HOS release tells us that this system has been built using build-root version 2015.02. In this hard disk image I put a copy of the squashfs root file system of our sample Gemtek router on the folder /mips root, so we can execute the interesting binaries in this emulation environment. We can try to run the interesting assistant command included in the message center executable that manages the router. This command is used to generate the Wi-Fi password of our router. We can execute the same command we executed in the previous episode using the serial number of our router label and the last 6 charts of the SSID as parameters for the -H and -S options. But we receive the error that the library file libcmc.so has not been found. This is a custom development library that is not included in our root file system that has only open source components. We can use the ld library path environment variable to include at the end the root file system of our device in the library search path. In this way, if some library is not found in the usual places, it will search it in the root file system of our device. After having set this environment variable, we execute the command again, and we get the password of our router, but in mixed case. If we execute the same command as in the message center executable, we get exactly our router password. This means that our emulation environment is working. We can try to execute the shellout binary of our router, the binary that replaced the bin login, to see if in this environment it works as expected, because in the QEMU user mode emulation it didn't write anything on the standard output. We can see that now it gives a challenge code, as it does on the real hardware. Again, our emulation environment is working. Another useful possibility in emulating a firmware is to emulate the NAND EEPROM. In QEMU there are few boards with the NAND EEPROM, but I wasn't successful in using them. This emulation was so slow to be unusable, or I wasn't able to use the right parameter combination. Anyway, in building the kernel and root file system, it is possible to include a NAND SIM module in the kernel to emulate a NAND EEPROM directly in the guest system. This can be useful not for booting the system, but to load a specific file system image in the emulated NAND EEPROM, and then mount this file system. This can be done, for example, for UBFS or JFFS2 file system images. As an example, I put in the root file system of the guest, in the folder /mips-firm, the dump of the firmware partition I extracted from our sample router in the fifth episode of the series. To emulate the NAND EEPROM, we have to insert into the kernel the module NANDSIM with the modprop command. It takes some ID parameters to identify the NAND EEPROM. We can look at the web page shown, link in the description below, to understand what parameters to use. You can see that they are related to the NAND EEPROM size and is page size. These parameters and the ID value of the EEPROM are returned by the readID command that the bootloader and the kernel use to identify the chip. We can use multiple ways to understand what is the correct ID parameter. We can look if during boot on the serial console the bootloader or the kernel printed these values. In our sample Gemtek router, the bootloader and the kernel printed the shown lines during boot, containing the ID bytes of the EEPROM. In the modprop, we used the first 4 of these values. If this information is not printed during boot, we can identify the EEPROM path number, as we have done in the first episode of this series, and look at its datasheet to find the ID as shown on the screen. We can see that these values are the same values printed during boot. But if we don't know the EEPROM part number and don't have its datasheet, we anyway know that what matters for a correct emulation is to have the same NAND EEPROM memory size, the same erase block size, and the same page size. Usually this information is printed during boot as shown on the screen. We can use this information to match corresponding ID values from the Linux MTD page. In our case, for example, we have a 128 megabytes of EEPROM with a 128 kilobyte block erase size and a 2 kilobyte page size, so we can select the row shown on the screen. If nothing of this information is available, we have to try different EEPROM times with a trial and error approach. In our case, we can execute inside our guest the script setNANDSIM.sh. The first step is to load into the kernel the NANDSIM module with the modprop command. The 4 bytes passed as parameters are the ID of the NAND EEPROM we have seen above. The cache file parameter is optional. If present, this file will be used to store the content of the EEPROM. Otherwise, the EEPROM content will be stored in RAM. In our case, that our emulated board has only 256 megabytes of RAM, it is better to cache the value of the EEPROM to a file to not fill the available RAM. The parameter parts specifies the size of each partition in number of erase blocks. In our case, the erase block size is 128 kilobyte, so this parameter is the number of 128 kilobyte block size. Each partition size is separated by a comma. we have specified 9 partitions with the same size as in our Gemtech sample router. The NandSim kernel module has created 9 devices, one for each emulated EEPROM partition. Before writing anything on these partitions, we have to erase the partition with the flash erase command that takes as a first parameter the device name and as the second parameter the number of erase blocks, that in our case is number of 128 kilobytes block. Then we load each partition file dumped from our sample Gemtech router to its corresponding partition with the NandWrite command that takes as first parameter the device name and as the second parameter the file name. We know that the file corresponding to the 9th partition is a UBFS image file system. We want to mount this file system, and so we create a mount point /mnt/jffs2 with the same name as in our sample Gemtech router. We have to attach a UB device to the mtd device to mount this UBFS file system. This is done with the ubattach command. The -O option specify the volume identifier header offset. If you put a wrong value, you will receive an error, usually indicating the right value. Anyway, you can try with different values like 512 or 1024 and similar values until you will find the right one. The -M option specify the MTD device number, in this case A8 for dev MTD8. The -D option specify the UB device number, in this case 8 for dev UB8_0. We can finally mount our UBFS file system with the mount command. We can now execute this script. Wait till every partition has been erased, each partition has been loaded in the emulated EEPROM, and the UBFS has been mounted. We can now explore this file system. This is natively mounted in our emulation environment. This is a read-write file system. We can also write to it, but if we reuse the same shell script to restart the EEPROM simulation, we will overwrite it each time. You will find in the description below information and links to download this kernel, root file system image, and qr.sh script to run QEMU and emulate the Malta MIPS board. On the root file system, you will not find the folder /mips root and /mips firm because I cannot include the firmware of our sample Gemtech router without permission by its manufacturer. In this episode, we have seen the requirements that a debugging-friendly and reverse engineering-friendly emulation environment must have. We have seen the importance of a tool to automatically build the kernel and the root file system as similar as possible to our device. We have seen the various modes of QEMU emulation and how to emulate an entire system. In the next episode, we will see how to build the kernel and the root file system using build-the-root and how to overcome the dependency L that prevents an old version of build-the-root to run on recent Linux distribution. It will be, I hope, a really interesting episode. If you have found this video interesting, please subscribe, help this channel grow, share this video with friends interested in hardware hacking. Please click the subscribe button below and the notification bell to be notified when new episodes will be released. And don't forget to click the thumbs up icon. Please let me know in the comment below if you have found this episode easy to follow, or if you have found that my bad English is a big obstacle in understanding the content. Anyway, you can also enable closed captions or subtitles, where you will find everything I say in plain English. My scripting abilities should be better than my verbal abilities. Please give me feedback and don't hesitate to ask me questions, writing comments below. Let me know if you have suggestions to improve this channel or if you have enjoyed or not this video. Every comment, but positive and negative, is welcome. Thank you for watching. See you again on this channel.